In today's video, I will present different techniques for learning with spiking neural networks, and specifically their application for gesture recognition. I will start with an overview of different learning approaches. Then I will present an example of a two-stage training process, which makes use of two of the mentioned techniques. Finally, I will show how the two-stage training process can be leveraged to build a neuromorphic gesture recognition system. Neuromorphic systems take inspiration from biology of neurons and allowing low latency and low power applications. The system architecture that I will present today includes a neuromorphic sensor and neuromorphic algorithms, so-called spiking neural networks. The underlying neuromorphic hardware is Intel's research platform Loihi, and in the future, these approaches will enable low power, low latency, and adaptive systems, and specifically also human-machine and human-robot interfaces. Before we dive into learning with spiking neural networks specifically, we take a look at learning or training from the definition. So one of the most important and crucial steps in learning is the optimization of the network's parameters and weights. And therefore, a common definition of training or learning is the optimization procedure that adjusts the parameters of weights or network parameters to minimize a given objective function. Neftzi and Zenke also use this definition of training a neural network in their important work on surrogate gradient learning and spiking neural networks. Another important thing to introduce here are spiking neural networks. These networks communicate with spikes, so trains of binary impulses, like the brain does. A good definition comes from another foundation paper on the intersection of spiking neural networks and deep learning, and is the following. A spiking neural network is a neural network with a single-bit binary activations, so-called spikes, that encode information over time. So now we have a definition of a training procedure and of our underlying algorithm, the spiking neural networks. Now I want to talk about specific training approaches for spiking neural networks. The first one is shadow training. This means you train an artificial neural network and convert it to a spiking neural network. The main difference between these ANNs and SNNs lies in the level of detail, how they want to mimic the human brain. SNNs specifically target the emulation of the neuronal behavior and also the event-based communication via spikes. For ANN to SNN conversions, there are different techniques. For example, by interpreting the activations as spike rates, so the frequency of spikes, or by interpreting the activations as the specific spike times. The second training approach is direct backpropagation using spikes. Here, a global error backpropagation is performed using backpropagation through time to also incorporate temporal signals and surrogate gradients to be able to calculate a derivative for the spike function. This was introduced by Neftzi and Zenke in their already mentioned paper on surrogate gradient learning in spiking neural networks. And it enables learning of spatiotemporal patterns. The third approach that I want to present here is a bit different from there. What we saw in backpropagation using spikes is we have a global learning rule. But depending on whether the weight updates occur synchronous for the entire network or not, a learning rule can be global as the backpropagation using spikes, or it can be local. The local learning rules, they update the weights only based on spatially and temporally local signals. And this also enables implementation of more brain-inspired learning techniques. All these three approaches have different characteristics, and hence also the application scenarios where we want to use them are different. Now I will present a two-stage training process which makes use of both backpropagation using spikes and also local biological inspired learning rules. The direct approach that I'm proposing makes use of an event-driven camera. You can see one here. This is a bio-inspired technology where every pixel in the visual field responds asynchronously to increase or decrease in light and communicates the X and Y coordinates and also the time when this event occurred. The target hardware platform for the approach is a neuromorphic hardware. In this case, we have a digital one, but in generally, neuromorphic platforms try to physically or digitally emulate the behavior of neurons and an asynchronous communication between them in form of spikes. The proposed two-stage training process looks like this. So we have the direct SNN training in emulation mode to prepare the network for the rapid on-chip learning, which will happen on neuromorphic hardware later by using local brain-inspired learning rules. The network architecture is a spiking convolutional neural network consisting of convolutional layers, pooling layers, and densely connected layers of CUBA, leaky integrate and fire neurons. This is a widely used type of neurons and also a well-accepted abstraction level from the biological neuron behavior. Now we take a look at the first stage of our two-stage training process, which is the pre-training. Here we initialize the parameters of the network for the later stage of local on-chip learning. The technique that we use here is backpropagation with spikes. We emulate the spiking neural networks on GPU, which enables to make use of deep learning frameworks like PyTorch and their auto-differentiation tooling. We implement the spiking neural network as a recurrent neural network with binary activations and also a feedback connection to itself, so an internal state. The backpropagation with spikes algorithm also enables us to find solutions for the two challenges that are there when training spiking neural networks with backpropagation. It's first to incorporate the time in the optimization process. Therefore, we use backpropagation through time. The second challenge is that the spike derivative is ill-defined when it fires. And here we can use a surrogate gradient function to smoothen the derivative of the spike function. In this stage, we can also make use of large recorded datasets over which we iteratively optimize to find the best possible network parameters. The goal of this stage is to provide a feature extraction with good generalization, also to new data samples that were not part of the initial distribution. Here we can also see similarities to transfer learning, which is well known from deep learning. We pre-train a network on a large data set and then fine-tune it on few examples of our task data set. A more advanced pre-training technique here would be, for example, meta-learning, which is known as learning to learn. Therefore, the network really literally learns to learn, which means that next to the network parameters and weights, this approach also enables to learn the hyperparameters for the later stage of on-chip learning and enables even faster and better on-chip adaptation. Now let's dive into the second stage, the rapid on-chip learning. This stage is there to enable adaptability of systems to dynamic environments or new classes that are presented. And in the future, it can be really the approach to pursue. So what we do here is on-the-fly learning from few examples. So just in the gesture case, just a few seconds of presenting time. And as we want to implement this on neuromorphic hardware, we make use of the neuromorphic hardware's plasticity processor, which enables learning with local signals. So implementation of local learning rules. In order to prevent catastrophic forgetting in the network, we only update the weights of the last layer of the network. And therefore, we use an error-triggered delta rule, which was introduced by Stewart in his work on online few-shot gesture learning on a neuromorphic processor. And this learning rule is also called SOEL, and it updates the weights according to three components, which is first the task error, then a surrogate gradient function, and the synaptic pretrace. So using this learning rule, we can implement on-chip adaptation to new classes. And as this happens directly on the neuromorphic processor, it can be implemented with only a very low latency and energy overhead. And this means that we can learn new classes in real time during inference without interrupting the inference for specific learning procedure. Now we can take a look at the specific application that I want to present today, which is gesture recognition. Gesture recognition on edge devices has been shown using different kind of sensors. So radar, ultrasound, RGB, frames or videos, and also these event-based cameras. Our proposed system is also based on these Spiro-inspired event-based cameras and spiking neural networks as neuromorphic algorithms. The specific system requirements for a gesture recognition system on an edge device is that we want to have accurate recognition, a low power consumption. We want the system to be always on. We also want to have support for new or personalized gestures. And the system should run at a low latency and in real time. Our proposed system consists of three parts, which is at first the event-based vision sensor, which detects only luminosity changes and therefore leads to low power, low latency, and high temporal resolution and high dynamic range sensing of the visual field. The second part is a spiking convolutional feature extractor, which is pre-trained on GPU using the backpropagation with spikes algorithm with a large recorded dataset, and then ported on our neuromorphic hardware to be able to run at low power and with low latency. The third stage is the rapid on-chip learning layer, which is implemented using the neuromorphic hardware's plasticity processor, and it enables learning new gestures only from short demonstrations, which can enhance accuracy and also enable personalization of gestures. The pre-training can occur or can be done using general gestures recorded from multiple persons and also in different environmental conditions or also viewing angles. And then the rapid on-chip learning is really done for the personalized and task-specific gestures. This gesture recognition system, we can imagine a lot of scenarios where this can be used. One could be that it can be used as a gesture interface in consumer electronics, for example, in a coffee machine or in a smart TV. Also, it could be used for recognizing exercises at the gym, or also for recognizing instrument gestures, like playing instruments. And we can think of many, many more applications for this gesture recognition system. Here in our labs, we implemented a playful music demonstrator, which is able to recognize different instrument gestures and also changes the intonation of the songs accordingly. This demonstrator also has the on-chip learning capability, and you will see the setup and also how the demonstrator works in the following videos. Today, I presented an overview of learning techniques for spiking neural networks. In a two-stage learning approach, two of the techniques can be combined to enable high accuracy and on-the-fly learning. The presented neuromorphic gesture recognition system was designed using this two-stage training process, and it enables accurate, low power, and low latency and adaptive gesture recognition. There are a lot of specific application scenarios for such a gesture recognition system. And moreover, it can also serve as a role model for other use cases with similar requirements like robotics or space applications. If you're interested in other neuromorphic methodologies and algorithms, Feel free to also watch our other videos.